Good morning, good afternoon, and good evening, everyone. My name is Dr. Andres Ardila. I'm a technical services veterinarian for swine within the VMS team. And on behalf of Boehringer Ingelheim, it is my pleasure to welcome you to the second seminar of our Swine Connection series, featuring an update on porcine circoviruses of importance in pig medicine. We would have loved to have this meeting face-to-face, but with the current situation, we must ensure the safety of everyone. While we have been lucky in Australia with a small number of cases over the last few months, outbreaks still happen, causing lockdowns like the one that currently is affecting us in Queensland. However, we must move on and take advantage of the new normal, where we spend a lot of time in MS meetings or Zoom meetings, but also give us the opportunity to participate in seminars like this one, where you can share with experts from around the world from the comfort of your homes. Like we did last year with the seminar on respiratory pathogens of growing pigs, which was a huge success. So thank you so much for joining us, and we look forward to meeting you face-to-face very soon. Before we start the presentations, I would like to draw your attention to a tool that we will be using tonight, which is the Q&A tab. It can be found at the lower part of your screen. Please use to request any assistance if you are experiencing any technical issues during the seminar, or to ask any questions to our panel. I would like to now move on to share with you the agenda for tonight. As you probably know, we started just with this welcome and housekeeping, which will follow with Professor Joaquim Segale in a presentation on PCV2, current challenges in the diagnosis and vaccination, all that glitter is not gold. Then we will have a presentation by Dr. Oliver Duran, is PCV3 a swine pathogen or not? And then we will finish with a Q&A session. Our first speaker probably doesn't need an introduction, but I will provide a short version nevertheless. Professor Joaquim Segale obtained his DVM and a PhD from the Universitat Autònoma de Barcelona. He has been a diplomate of the European College of Veterinary Pathology since 2000 and of the European College of Porcine Health Management since 2004. He's a full professor at UAB and a researcher at the Institute of Agri-Food Research and Technology in Spain. Professor Segale has been investigating swine diseases for over 28 years and have published over 350 peer-reviewed publications. And tonight we'll share his presentation titled PCV2 Current Challenges in the Diagnosis and Vaccination. All that glitters is not gold. Thank you so much, Dr. Segale, for joining us, and the floor is yours.
Thank you very much, Andres, and good evening to everybody. I'm very happy to share this time with you. I really hope that you will enjoy the presentations and the discussion afterwards. You will see that the title is slightly different, but in a sense, it contains exactly the same that Andres already introduced. Because at the very end, we are in 2021. We know this disease, or the diseases caused by PCV2, for more than 24, 25 years already. And we have been benefiting for the use of vaccine for more than 14 years now. So from this point of view, I would like to focus on what could be our concerns in 2021. Well, in fact, the most important, or the current challenges that I considered, is based on those three major issues. The first one is related with diagnostics. Because we are relying most of the time to certain laboratory techniques, and I would like to emphasize the importance of getting back to the basics, because yes, we have excellent laboratory techniques, but it's very, very important, the veterinarian and the follow-up of the situation under clinical conditions for the diagnostic purposes at the very end. We are also sometimes vaccinating with excellent results, which is what is expectable, really. However, some farms, I would say very few farms, in spite of vaccination, they are being diagnosed as porcine circovirus 2 systemic disease, the former known as PMWS, Porcine multisystemic wasting syndrome. So why this happens? And we will discuss a little bit on that. And finally, even it's much more on a theoretical basis, but of course it's something that is happening under field condition, there is a variety of genotypes of PCV2. So what does it mean? Which is the importance of those different genotypes? So let's start for the diagnostic issue. And I'm introducing this subject because it's not unusual during the last 5-6 years to receive calls from veterinarians saying that, hey, I'm vaccinating against PCV2, my piglets, but I got some PCR results, quantitative PCR results, and I got the results of 10 to the 7 DNA copies of PCV2 per ml of serum. Is my vaccination works properly? Am I having a problem? Of course, the first issue, based only on such data, I usually answer with a very typical Spanish sentence that you will understand rapidly, which is ni sí ni no ni todo lo contrario. This means neither yes nor no, nor quite the opposite. In other words, if you're vaccinating and you got results on quantitative PCR to 10 to the 7, this does not really mean anything special. This is something that you will have to investigate. This doesn't preclude your vaccination doesn't work. And it's very important at this stage to differentiate what is really an analytical result from a particular laboratory technique or a disease diagnosis. Within the disease diagnosis, the clinical part is fundamental, and this is very important. In fact, the main criteria, especially the individual criteria for diagnosing PCV2 systemic disease, are well known since 1999, so long time ago. It's true that over the time, the diagnostic criteria have been changed a bit, especially introducing what we call the herd case definition. And this is an old paper from 2012, but it was the European project that we were involved with, in which we participated in order to define what a herd case definition means. And to our understanding, especially at that time, might be nowadays could be slightly modified, but in a sense will be exactly the same. We compile with a PCV2 systemic disease diagnosis when you have two major herd criteria. First is increase in post-weaning mortality. Why we use the mortality as a criteria? Because mortality can be due to many potential causes. However, it's very clear that in the systemic disease, one of the major outcomes when you have the severe problem in farm is an increase in mortality. And this is very objectivable at the very end, so it can be very objective. Of course, this increase in mortality must be compared to the previous historical records in the farm and should be a clearly significant increase. The second part of the diagnosis, which gives you the specificity of the diagnosis, is the confirmation of the individual diagnostic criteria for the animals which are suffering from the disease. And the point is to at least confirm such laboratory criteria, clinical and laboratorial criteria, in 1 out of 3 to 5 animals at least. The typical 3 criteria at individual level are very clear. We need to see clinical compatible signs. This means mainly wasting or respiratory problems. Sometimes there's diarrhea. There's a myriad of potential clinical issues related. But the most important ones are histopathology of lymphoid tissues. We have to see the moderate to severe lymphocyte depletion and granulomatous inflammation. And third, to detect PCV2 in those tissues. Those are the diagnostic criteria that we know since 1999. And those diagnostic criteria have not changed. So if you want to confirm PCV2 systemic disease, you should go back to this. However, it's true that the histopathology expertise in some countries is not easy to be found. This is not the case of Australia. Certainly, you have excellent places in which histopathology and PCV2 detection can be performed. And the practical tips to diagnose the disease is basically to target lymphoid tissues, and especially not chronically affected animals, but those animals showing no more than 1 week since starting of the symptoms or the clinical signs. So the peak on the left-hand side would not be appropriate for diagnosis, because even this animal may have been suffering from PCV2 systemic disease. Probably he's recovering, not clinically, but from a histological point of view, the lesions might be gone or would be minimal. So those animals just starting with the wasting, with the loss of weight, would be the ideal ones. So we should say that the basic elements for PCV2 systemic disease diagnosis have not changed. And very important, PCR, quantitative PCR, detection of antibodies does not allow you to establish the diagnosis. By the way, and you must understand me clearly, those are excellent, excellent techniques to monitor PCV2 infection under different circumstances. So those are very useful techniques in all cases, all right? But they do not provide you the diagnosis of the disease. And of course, the major utility that they may have is to monitor the infection and eventually also the vaccination, or even the best moment for vaccination. So you have to take into account that those tools will be excellent for this monitoring. And yes, this is a talk about porcine circovirus, and the older ones in the audience probably may know this movie, The Good, the Bad, and the Ugly. If I'm asking to which type of movie is, probably, and just looking at Clint Eastwood here, it's clear a Western, right? So this is a Western. And now I would connect a little bit the Westerns with pigs. Let me do in a very strange way, probably, but probably you have heard as veterinarians about Western blots. Western blots are analytical techniques basically used in molecular biology and also in immunogenetics that allow to detect specific proteins of tissue or of extract or something like that. So I don't know if you have ever seen how a Western blot looks like, but those are, and this is the comparison with the Good, the Bad, and the Ugly, the movie, how a Western blot looks like. And look, when you have a very good Western blot, you perfectly see the bands there indicating the presence at a given molecular weight where the protein is. So this is a very good Western blot. This is very bad. Doesn't discriminate anything. Here you have several bands and several molecular weights. It is really difficult to understand what's going on here. And the ugly, this is a disaster. So as a Western blot, if you are in the laboratory and you are doing a Western blot and you obtain a picture like that, this means start again from the scratch because nothing works here. Okay, so let me go there in the 3 kinds of PCV2 lab analysis based on the clinical outcome. And you will see that we have also the good, the bad, and the ugly. When you have a clinical outcome, so this is represented by the wasted pig, as you can see here, and the quantitative PCR is 10 to the 8 copies of DNA of PCV2 per ml, then you are almost in the right track that this is a PCV2 systemic disease for sure. So this is the good. So PCV2 or quantitative PCR for PCV2 is good enough to diagnose the condition. Okay, at least this would be your appraisal based on what you have here. But remember, you will have probably the bad and the ugly. And what's the bad? You have the same wasted animal in really bad clinical condition, but then you got 10 to the 4 copies or 10 to the 3 or even negative. How do you interpret that such result? Is it a problem? Is it not a problem? Might be this animal is too chronic or basically is affected by another condition, which is not PCV2 systemic disease. So this, of course, offers a complication in terms of interpretation. And the ugly one, you have an excellent, healthy or apparently healthy pig with 10 to the 8 copies per ml. Of course, since we have established a kind of threshold of the PCR, might be, one may say that 10 to the 8 should be a case of PCV2 systemic disease, but clinically, the animal is healthy or apparently healthy. So with this, I would like to highlight how important it is to keep a look on the peaks. And even this sounds very basic and might be even stupid. Sometimes we are relying too much on laboratory analysis to perform quantitative PCR. I want to know which is the amount of virus which is present there, when the important issue has to be told by the peaks. So please, leave the peaks explain what's going on, and then act in consequence in terms of establishing kind of diagnosis. And this famous 10 to the 7 copies of ml, it comes from a couple of works. One of them was from our laboratory that was performed more than 15 years ago, in which we took animals showing the typical systemic disease lesions. However, we took the ones with mild lesions, moderate lesions, and severe lesions. Remember that for establishing a sound diagnosis of the systemic disease, we use animals with moderate and severe lymphoid lesions. Well, each dot represents an individual animal. And what you see on the y-axis is the amount, in terms of logs, of copies of PCV2 nucleic acid per ml of serum. So if you look at here, the animals which are diagnosed as really systemic disease, the mean is 10 to the 7, slightly more for the moderate ones, and almost 10 to the 9, slightly more for the severe ones. So this allowed to propose at that time that probably whatever animal with a quantitative PCR result over 10 to the 7 would be eligible for a systemic disease diagnosis, while the ones below 10 to the 7 probably would reflect a subclinical infection. However, this is good from a population point of view. So it's a groupal approach. However, at individual approach, you can see that there's animals that from a pathological point of view and clinical point of view would be diagnosed as the systemic disease. However, they are below the threshold of 10 to the 7. And even less, there are some animals which are, especially those the two here, which are over 10 to the 8, but they were healthy, at least no moderate severe lesions were observed. So for the reason I want to emphasize that quantitative PCR is a very good technique, allows monitoring, even allows, of course, giving an idea of the amount of virus present, but it's not a direct measure of having a disease. The different thing is it a direct measure of losing weight or not progressing in terms of average daily weight gain as wished? This is a different issue. And of course, we can discuss afterwards. And another very important comment, not all quantitative PCRs are equal. This is a work from a PhD thesis that we conducted here at Crescent many years ago, and we compare the quantitative PCR that we were using together with another one that they were using in a Danish institute that at that time we were working together. And you can see that when you compare the viral load of laboratory 2 or the viral load of laboratory 1 using exactly the same sample, so each point means a different sample, but it's the same sample tested by both laboratories. So you can see that while, for example, this sample by laboratory 2, it was 10 to the 6.2, for the other, it was 6.2 as well. But others were completely different in the sense that this that was 10 to the 10 here, it was almost 10 to the 12 or 10 to the 11 here. In fact, we observed that it was a systematic difference of 1.4 logs plus minus 0.6 per each of the sample as a mean. What does imply that for, let's say, veterinary purposes? That depends on the PCR I'm using, might be, my result will be 10 to the 6, but the same sample in another laboratory could be 10 to the 7 or 10 to the 7.4. But of course, if we are considering 10 to the 7 as a threshold, then one would be diagnosed as systemic disease and the other not. And of course, everything depends on the technique. So this threshold of 10 to the 7 is not applicable to all quantitative PCRs existing so far. It was potentially, and I mean from a epidemiological point of view, applied to the population for that particular quantitative PCR. For example, one of the quantitative PCRs mostly used worldwide nowadays, which is the one from Thermo Fisher, which is a specific trademark, the amount of virus that it's able to detect is much higher than the one of the PCR in which the 10 to the 7 was proposed. So probably the 10 to the 7 from that particular technique nowadays is 10 to the 8 or even more. So it's very important to take into account which is the technique we are using. So another question performed by many veterinarians is, do we have any alert limit to take into account in order to be, let's say, concerned about the potential involvement of PCV2 in a problem? Well, by ELISA, certainly not. Serology tells you the presence of antibodies against PCV2, could be IgG, could be IgM, but it doesn't tell you about the problem or no problem. It simply says that PCV2 is circulating, or eventually that those antibodies may come because of the vaccination. Quantitative PCR in serum, well, it has been established this 10 to the 7, but with all the conditions I just mentioned. What happens if you are doing or performing the quantitative PCR in lung or lymph node? Well, by definition, the amount of virus in tissues is much higher than in sera. So a 10 to the 7 in sera would be equivalent to 10 to the 9 to 10 to the 10 in lung or lymphoid tissue. So take this into account. And what could happen, the quantitative PCR in ropes? Certainly there's no correlation at all with presence of disease or not, independently almost of the viral amount or the viral load you can detect. So are you sure that if you have 10 to the 7, you are having much more problems in one farm or particular farm? Of course, the ideal situation would be to have less amount of virus possible. But as you know, PCV2 is an ubiquitous virus at the area. So the current needs nowadays, 2021, for diagnosis is basically in those farms in which, of course, they have a compatible clinical picture of PCV2 systemic disease. Also to rule out the cause of wasting in post-weaning pigs. And very importantly, when vaccinations expectations are not met, or you may have a suspicion of what, between commas, I call here vaccine failure. And this connects with the second part of the talk, because what happens if I'm being diagnosed as the systemic disease in spite I'm vaccination? I'm doing the vaccination, and theoretically I'm doing a good vaccination, applying it to the right place with the right amount, etc., with the right conservation of the vaccine. What's going on here? Well, let me explain a little bit how PCV2 vaccination has been evolved over time, and this may apply to certain parts of the world, not all. But for example, the vaccination of the sow was the starting point in Europe. Even it was switched rapidly to the piglet vaccination, that's for sure. But the sow, it was our starting point here. And in the rest of the world, it was mainly piglet vaccination. After some years, piglet vaccination was accompanied by gill vaccination in the acclimatization period. And this was due to the lack of evidence of seroconversion during the fattening period in a number of farms or in a number of batches, not always all the farms, but on a batch level. And even nowadays, depends on the farm, or even in some countries, piglets, gills, and sows may be able to be vaccinated. What I would like to highlight here is, by means of vaccinating one or the other collective or several collectives, what we do is to change the epidemiology of PCV2. And this is important. Why? Here's an example I just mentioned before. This is a study that we conducted basically with animals with high antibody titers at 3 weeks of age, the age of vaccination at that particular farm, and animals with low amount of antibodies. Well, we followed them up after vaccination, and our idea was to see the performance of the vaccine in such scenarios with high amount of antibodies or low amount of antibodies at vaccination. However, look at the serological curves. those animals did not seroconvert. Even we detect by PCR, those are the columns here, in some animals, the percentage of infected animals in both groups was extremely low, extremely low. So the infectious pressure was very low and do not allow for a general seroconversion of the animals. What happened when reaching the point of a slaughter? Of course, those animals are going to slaughter and they are sacrificed and that's it. But what happened if a percentage of those animals are taken as a gilts, as a reproductive stock? Well, those animals are negative, presumably. So even they were vaccinated at 3 weeks of age, when reaching the gilt status, those animals are seronegative or almost seronegative. Moreover, if you look at your particular farm and you try to see the, let's say, the titer, but we are not measuring titer with ELISA test, but we are measuring or absorbance or SP values or OD ratios, etc. But you measure these values by serology, you will see that probably there's a significant difference in terms of amount of antibodies, depends on the parity or depends on individual. In this case, by Olivier et al. 2018, we observed that parity 0, the gilts, they were quite well provided in terms of antibodies, but from parity 1 to parity 8, it was quite a huge variabilities, with some animals under the cutoff threshold offered by the ELISA test. So some animals were negative. Here you have one in parity 1, in parity 4, parity 5, etc. And that amount of antibodies was very variable. So what does it mean here? That in a farm, especially when looking at the reproductive stock, you have subpopulations from a serological point of view. Animals with high antibody values, animals with low antibody values. And those are intermingled, of course. So if you have such a scenario in which your gilts could be negative and you may have subpopulations in your sow farm, it's very likely that probably gilt and sow vaccination may be advisable in a number of cases. But why I said that the epidemiology has changed by means of using vaccination systematically? Look at the pre-vaccination scenario. In that situation, most of the sows were completely seropositive, and sometimes with a high antibody values. This means that the piglets received the maternal-derived immunity, and the natural infection just occurred when such maternal-derived immunity waned. What happened? If the animals were genetically susceptible, if the risk factors applied in that particular farm, a proportion of them may develop the systemic disease, which are represented here. The age of presentation was very variable. Sometimes we observed animals with 8, 9, 10 weeks, but also 15 weeks, 18 weeks, etc. It depends on the farm conditions. And the rest of the animals were apparently healthy. And when I say apparently healthy, I must say that, and we know now, after the vaccines came into the market, that those animals, in spite of being apparently healthy, they were subclinically infected. Those animals didn't grow based on the potential they had. Okay, but this is the pre-vaccination scenario. Let's say that we start vaccinating the piglets. Well, the sows, of course, are still mostly seropositive, with more or less high antibody values. The vaccination of the piglets in presence of maternal-derived immunity worked very well, allows providing acquired immunity to those animals still in presence of the maternal-derived one, so it was a complete well fit of the window that would allow infection. So from this point of view, the cases of systemic disease disappeared and the animals were healthy, and even the subclinical infection were under control. So animals suddenly growth much better with 10 to 40 grams per day more. Here is where the money is at the very end. So you have to take into account rather than in the mortality, and the clinical picture disappeared. So that's what's the reason why from the very beginning, the use of vaccines apparently implied a big change, a complete change, and everything worked. It was marvelous, really. Of course, if we are continue vaccinating, and this is what could happen if we are not just doing such vaccination in the farms that we selected because they had particular problems, but I'm vaccinating elsewhere, what could happen here is that those healthy animals with the subclinical infection under control barely circulate the virus. So the infectious pressure, the real infectious pressure, was rather low. This is what we have shown with the graphic in which you see the no seroconversion of those animals vaccinated at 3 weeks of age. And this implies the generation of a proportion of seronegative replacements, the gills in principle, at least in the mid-long term. And this probably it could happen in most, if not all, the farms, really. But this implies presence of PCV2 subpopulations. What happened here in such a scenario in which you have the such subpopulations? Well, sows, and of course, first of all, the gills, but remember on the serum profile or the antibody profile that we have seen before, we have subpopulation at different levels, not necessarily gills. In some farms, it will not be gills, it will be the all parity ones. It depends on the case. So if we have animals which are seronegative or almost seronegative, or some animals which are seronegative, there's risk of sow infection. And if we have risk of sow infection, of course, there's risk of early infection of piglets. And what happened? If there's infection in the sows, basically because there's almost no immunity, this means no transfer of maternal-derived immunity. So the piglets are unprotected mainly, or poorly protected, or with a very short duration of maternal-derived immunity. If I got infection during the lactating period and I'm vaccinating at weaning or at 3, 4, or 5 weeks of age, what happened? That sometimes the vaccination occurs too late because we already got the infection even before or at the time of vaccination. And this means that we appear or we observe the appearance of new cases of PCV2 systemic disease, in spite we are vaccination. Of course, this is the big surprise by the farmers. Come on, I'm doing the same than always, and now I have problems. What I'm doing wrong? Might be you are not doing anything wrong. Simply, you have to reschedule probably your vaccination program. Because what happened here is that those cases which are systemic disease are early cases because of those early infections. And we have been observing cases of the systemic disease with 7, 8, 6 weeks of age in a number of cases. Very important to note as well, this is a scenario in which I'm vaccinating, because I'm vaccinating my piglets and eventually my gills, or not, but my piglets for sure. In such a scenario, what we really see is the tip of the iceberg. We are observing this because suddenly we reach the conclusion that the vaccine that used to work extremely well, now it doesn't work as well as it should be. Well, the point is that the vaccine works as well as always. The major problem right now is that we are vaccinating too late in those animals. This is not a vaccine failure. This is not vaccination failure. This is a problem of the timing of your vaccination. And this is the thing that you should reschedule. But very importantly, we are human beings. And as human beings, we are only focusing with our problems. Might be in 90% or 95 or 98% of our farms, everything works very well. But we are keeping the attention on the ones that doesn't work well. And then it looks like that the vaccine doesn't work. That might be the same vaccine you are using in lots of farms and it was perfect. So this has not changed. More importantly, for having those early cases of systemic disease, it's not enough to have early viral circulation. You need to have a susceptible genetics, and probably you need to have some risk factors, because the risk factors that we used to talk with the Madec point plan, etc., still applies. PCV2 systemic disease is still a multifactorial disease. This has not been changed over the years. So how can we solve this scenario? Basically, we should reschedule the PCV2 vaccination. One possibility is to vaccinate sows and gills. With this, we obtain certainly herd immunity. This may imply, depends on when do we vaccinate these sows and gills, that we have to change the timing of vaccination of the piglets in order to avoid potential interference with maternal-derived immunity. However, this interference is something debatable, definitely. Another way, at least in the short term, that could work is early vaccination of piglets. Very important. This is the typical case in which you should monitor what's going on. So to detect PCV2 by PCR, quantitative PCR, and detect antibodies by ELISA basically could be of benefit and help in assessing the right timing for vaccination. And another very important point, be sure that there's not a kind of immunomodulating co-infection at the time of vaccination, especially Porcine virus. I know Porcine virus is not a problem in Australia, but it's a big problem in many countries all over the world. So if you have other immunomodulating pathogen at the time of PCV2 vaccination, this might create a significant problem. And let me finish with talking about PCV2 genotypes, because when you are asking how many genotypes exist with PCV2, well, everything depends on how do you define what the genotype is and how do and which are the definition criteria. Let's say that from the very beginning, and I'm talking now around the year 2000, where the number of sequences of PCV2 were very limited, at least 2 genetic groupings were observed. So it was quite clear. So some sequences were in one group and some others in another group. And we start discussing about the names of those genotypes. In fact, such discussion was a big mess all over the world until by 2008 we agreed in a common nomenclature, and is what we should call PCV2A and B. So those were the 2 big groups that we observed from the very beginning. In fact, PCV2A was the very firstly described one and was associated with the systemic disease, but in its appearance as a sporadic form. The other group, PCV2B, was mainly associated with the big outbreaks, big disease outbreaks associated with the systemic disease, and all over the world. And in fact, it was amazing because in all countries in which this was studied, it was observed that the transfer from a sporadic form to epidemic form of the systemic disease coincided with a genotype shift from A to B. So the prevalence of PCV2 genotype A decreased and the PCV2 genotype B increased substantially. Of course, in the meantime, we got some information from Denmark that in the recent years has been detected in other countries as well, but a very strange genotype, which was named C, and PCV2C was just detected retrospectively during the 80s. In fact, afterwards, it has been detected in Brazil, in China, and probably related with or wild pigs or in pigs that have been isolated for a period of time. But nowadays, the most common one is PCV2D, not B. In fact, PCV2D was described as a mutant of PCV2B and was linked to vaccination failure. However, those cases of failure in spite of vaccination were never demonstrated that it was due to the new virus or the new variant, because this new variant or genotype at the very end looks to be as pathogenic as PCV2B or even PCV2A really. In fact, difference in pathogenicity or virulence between those genotypes have never been demonstrated so far. And regarding this genotype diversity, you can see here PCV2A, B, and D, which are the most common and frequent genotypes. This is not the really frequency, but can be interpreted as frequency. You can see that around the year 2000, it was a kind of shift in which the dominating was A, and suddenly it was B, and this was related with the major advent of big outbreaks. And then another one which occurred around 2010 and forward, which from PCV2B as a dominating one, we pass to PCV2D. Well, while here the epidemiological scenario was to switch from, let's say, sporadic problems to very severe generalized problems, what we observe here is the implementation of massive vaccination. When I say massive, I mean all over the world in a huge percentage of animals in most of the countries. However, the vaccines used mostly at that time, they were based on PCV2A. Nowadays, we have other vaccines in different parts of the world based on different genotypes or even a combination of genotypes, but mainly PCV2A based vaccines are the most important ones still. Well, so we have confirmed such a genotype shift from B to D, and nowadays D is the most frequent genotype all over the world as well. Why this kind of classification is varying over time? Basically, because first of all, we had few sequences, and to divide in those two groups was relatively easy. But as long as the sequencing capacity increased over time and all over the world, the number of sequences that fall in between increased, and increased to the point that to do a separation in two groups was really not possible. And at a given time point, another new proposal was for 4 different genotypes, A, B, C, D, but rapidly they appear what they call PCV2E or PCV2F. So this implied that by a couple of years ago, together with a colleague in Italy, we proposed a new genotype system that, of course, was friendly with the previous one. So what was A still is A, or what it was D is still D. But taking into account all the sequences existing in the gene banks, we observed that at least 8 different genotypes can be defined. And furthermore, another study that appeared in the US in 2019 proposed another new genotype, I. So nowadays, probably we should conclude that we have at least 9 different genotypes circulating all over the world, or at least sequences from 9 different genotypes do exist. Even though PCV2D is still the most prevalent one, followed by B and A. It could happen that in some countries might be B is still the predominant, but I'm talking worldwide. And it's very likely that the number of genotypes will increase in the future, because such kind of classification is in permanent revision, really. And finally, to finish this presentation, just to indicate that in spite that we have a number of genotypes, we are talking about 9 nowadays, even there are 3 which are predominant, but 9 overall. And even there are some very specific immunological differences among them, basically at monoclonal level. So we can generate monoclonal level antibodies that are able to find certain epitopes of certain genotypes that do not recognize the same epitope of another genotype. So from this point of view, there are some slight differences in terms of epitopes and then in terms of immunological response. But remember that the immunological response is polyclonal in terms of antibodies, and we have a cellular immunity associated. Even we usually don't measure it, but it's very important as well. So the conclusion of the work that we performed also with Dr. Franzo a while ago is that porcine circovirus 2, even we have multiple genotypes, probably we are still having one single serotype, which is important because this offers you the indication that there's cross protection among the different genotypes. So what we considered, and this is taken directly from the paper, is that although that genotype variability is likely to increase in the future, because this will happen, is something that we don't have any doubt, the existing data to date indicates that cross immunity is present at least among the major genotypes. In fact, if the question is, do you have an isolate of PCV2H? We don't have it. Basically, we have isolates all over the world of PCV2A, B, and D. And of course, very important, this is to date. But anyway, to date at least, it seems that the vaccine-induced protection based on PCV2A is warranted. Said in other words, current vaccines in the market based on PCV2A are still able to protect against the infection by other genotypes. A very important question would be, but is it as good a genotype A based vaccine as a genotype B or a genotype D based vaccine? Is exactly the same? Well, you have to think that we are dealing with very good vaccines, very effective vaccines. So to demonstrate that one is better than the other when all of them are very efficient already could be very, very difficult. But anyway, I believe that this is a kind of good message that the cross protection still exists, at least today, and this will hopefully will be maintained in the future. But for this reason, it's very important to monitor how the PCV2 may change over time, because escape mutants have been described for many viruses and many diseases. So why not could happen in the future with PCV2? But to date, at least, we don't have it. And with this, I will finish. Thank you very much for your attention. I hope it has been of interest, and happy to discuss in the question and answer session. So thank you very much. Andres, the floor is yours.
Thank you so much, Professor Segale. That was a really nice presentation, and some of the questions that I had myself were probably answered during your presentation. So I appreciate how easy it was for you to detail all of them. Thank you so much. We'll just move on with our next presenter, and we will have all the questions that you have typed on the chat at the end. I would like to invite now our second presentation, which will feature Dr. Oliver Duran. Oliver is a veterinarian dedicated to the prevention of swine diseases through management, biosecurity, and vaccination. Oliver obtained his DVM from the Universidad de Zaragoza and his PhD from the University of Liverpool. He has been a diplomate of the European College of Porcine Health Management since 2006, and his professional experience include roles in private practice and academia in the US and the UK. In 2011, he joined BI, where he currently holds the position of leader of the Global Swine Technical Team. And the title of his presentation is PCV3 a swine pathogen or not? Thank you, Oliver, for spending time with us, and I will leave the floor to you.
Thank you, Andres. Good afternoon, good evening, everybody. I hope you can hear me okay. I think Kim needs to stop sharing before I can share my screen. Hopefully you can see my screen now.
Yep, it's all good.
Great, great. Well, thank you, Andres, for your invitation to this webinar, and thank you for all of you for joining us today. I will try to give you an update about PCV3 and really answer a key question that we had, if some of you remember, when PCV2 was kicking off, and maybe try and shed some light into this question: is PCV3 a pathogen or not? Let's go through a little bit what we do know. So in regards to the virus, it's important that we understand that this PCV3 virus, based on its analysis to date, meets the criteria for a new species within the Circoviridae. While it's in that same family, it really doesn't share a huge amount of identity with neither PCV1 nor PCV2, around less than 50% at the genome level. When you look at the capsid protein, which is the key element that the immune system recognizes in the pig, PCV3 and PCV2 share only 37% identity at this protein level. So again, pointing towards a direction of this being a different virus to PCV2. It was first reported in the US in 2016 in some swine herds there, and really reported through the use of next generation sequencing to identify this novel virus. What's understood about the virus globally, you will see that it has now been described many, many parts of the world is that, like those in the US, they are pretty similar genetically. So they share around 98% identity. So there is the appearance of a certain genetic stability for this virus. To date, and I'm sure this is already out of date because the literature is very active on this, it has been detected and described in the US, in China, Thailand, South Korea, Brazil, Italy, Germany, UK, Sweden, Denmark, and Spain and Poland. So really, it appears ubiquitous globally. And it's also widespread when you look at prevalence within a country. So a study from the US in 2018 found that it was really widely spread across herds in the US. Recently, Dr. Segale published a study showing it was also widespread around Europe. So this is not unique to the US. And the other thing that is reported in the literature is that, as you would expect, commonly it is found together with other endemic pathogens like PRRS or PCV2. I say this because I think this is the experience of many researchers. Once they start searching for PCV3, it's pretty much everywhere. As I mentioned, it's been described in a long list of countries already since it was first described. And it's even been found in collections of samples that were banked in different countries, much, much earlier than 2016 when it was first described as a potential pathogen. And the earliest it has been found looking at retrospective sera or tissues was in 1967 in Brazil. So it's probable that this virus has been circulating in pigs at some level for quite some time without really being identified as a pathogen or otherwise. When we look at the situation in more detail, this is a paper that one of the colleagues of Professor Segale published a couple of years ago. It was identified broadly in a number of herds across Europe. This was a sample of sera from finishing farms across many European countries. And there it was found in really a large number of animals in this population and in a large number of farms within that population that was analyzed in this study. And in this case, interestingly, compared to what the literature had said before, co-infections of PCV2 and PCV3 in serum were rare. And the authors conclude that the circulation on these herds, because again, this was just finishing pig serum, appeared to be at different epidemiological pictures. And the other thing it showed is a relatively homogeneous genetic picture across Europe. So let's go into the part that's really interesting. So we've identified a virus at that stage until fairly recently, could not grow it. These were all genetic detections, either through next generation sequencing or by PCR eventually. And authors start associating this finding of the virus with a clinical picture on the farm. And this is just a very short overview of some of the diseases that have been associated with PCV3 detection, whether it's multisystemic inflammation, PDNS, perhaps reproductive failure. There has been some descriptions, particularly in Asia, related to respiratory disease cases. And then where the majority of the literature is pointing to is towards very specific reproductive failure cases, focused mostly on stillborn and mummified piglets. And even there's 2 publications suggesting an association with congenital tremors. And for sort of for pathologists and veterinarians in the field, congenital tremors is one of those diseases where every new virus that comes up gets assigned as the causal element for congenital tremors. So not unusual. The problem is that in most of these cases, there's either other pathogens detected, the virus PCV3 is detected, but the relevance of that detection and association to direct lesions has not been shown. And so it's quite difficult from these case reports, to really conclude firmly that there's a causal relationship. Really, it's not until fairly recently that we have very strong data associating the detection of PCV3 to clinical syndromes or clinical disease. One of those papers is an excellent paper published in 2019 or 2020, I can't remember now, that looked at a very specific collection of cases. And they did this for a period of time using predefined case definitions. They described 22 reproductive failure cases in herds in the US where they could not identify lots of the typical pathogens that you associate with reproductive failure in the US. Neither PRRS nor PCV2 nor parvo were found. They detected PCV3 not just by PCR, but also by in situ hybridization, which is a technique that allows you to identify nucleic acid material from the virus actually in the tissues, in the lesion areas, or also by next generation sequencing. This is a technique that allows you to detect really everything that is present in tissues potentially. And they associated those findings with lesions and with very specific clinical signs. In these cases, they were typically associated with low parity sows or gilts. The main clinical finding they had was increased mummified fetuses and stillborn, and the firing rate was reduced. They also describe less cases, but well-defined cases in piglets. So 11 cases in weaned pigs in this kind of nursery phase between 3 and 10 weeks of age. And the clinical picture was variable here. Occasionally some acute deaths, some poor doing pigs, maybe some dermatopathy type lesions, some skin lesions. And here again, they were able to exclude some of the typical pathogens associated with these clinical pictures. No PRRS, no PCV2 detected. And then there was 3 perinatal cases, all of them in startup farms, where they saw these congenital tremors, these shaker pigs. They identified the virus in blood vessels in the brain. So there was some inflammatory lesions associated with that. And the virus was detected in those lesions. And they also found myocarditis in these cases. So we're getting closer now to really associating, a cause and effect type association. Also, very, very recently, the virus has been cultured in the laboratory. So until then, until 2020, there's no description. Two labs separately did this, one in Korea, one in the US, have been able to culture virus from affected tissues. And then, even though it's quite difficult and the virus load that they can generate through viral culture has been quite limited, they have been able to both grow up virus in culture, and then in this study in Iowa State, they were able to replicate some of the histological elements of the disease when they infected colostrum-deprived cesarean-derived piglets. So much closer now to fulfilling Koch's postulates and being able to essentially reproduce the disease in the lab. So let's go through that a little bit. This paper from Iowa State in 2020, they were able to isolate 3 PCV3s from these cases that I described earlier. They were also from Iowa State. They were able to grow it in virus in cell culture, and this was then confirmed by detection by PCR, by immunofluorescence, and in situ hybridization. So powerful techniques to demonstrate that culture included the virus. And then, as I said, in a very small scale, they were able to reproduce or replicate PCV3 in vivo in pigs under these experimental conditions. Viremia was detected very early, so 7 days post-inoculation, and by 28 days, all 8 of these piglets were viremic. They did also detect an immune response to this infection, so this was not just that you were still detecting the original inoculum. There was a response, an immune response from those pigs in a proportion of those. And in the duration of the study, they were not able to detect IgG at that time, but they did detect IgM antibodies. Then, when they euthanized these pigs and looked under the microscope, they were able to show histological lesions that were very consistent with this multisystemic inflammation that has been described in some of the case reports that I shared earlier, particularly in the heart and in around blood vessels. And they were able to then show that the virus was replicating by detecting it by this in situ hybridization technique. Clinically, if you looked at these pigs grossly, there was really no evidence of disease. So these pigs appeared normal, but when you looked at lesions, you could detect lesions. So I'm going to focus a little bit on the reproductive disease, because as you saw from the case reports, that is the area where the weight of evidence is most significant. And to show you this, we've got the study from the US that I shared earlier on with 22 very well described cases. And then very, very recently, again, Kim's lab demonstrated, looking at reproductive failure cases in Spain, we're able to confirm from aborted fetuses and stillborn piglets PCV3. If you look at this table, you can see that there was other pathogens detected in this study, but there was a considerable number of these cases, 16 or 30%, where they found only PCV3, and they found it at a pretty significant rate. I'll show you that in a second. And really, it was also found in association with other infections capable of causing these clinical signs, where the picture is not as clear-cut. And curiously, for a country like Spain, where PRRS is endemic and causes a lot of problems, PRRS was not a major player. What I think is relevant for Australia, where you don't have PRRS, is that PCV3 has also been identified in mummified piglets or mummified fetuses in Brazil. So Brazil, like Australia, is free from PRRS to date. And here, in their analysis of this series of mummified cases, they again identified PCV3 either in combination with other typical viruses that cause mummies, like PCV2 and parvo, but also in some cases in an infection by itself, PCV3 alone, in 4% of the cases. So again, is suggesting that for sure we should include PCV3 in our list of differentials when we've got an increase in the level of mummified piglets in the herd. And I use this is a chart that we've used a lot to describe reproductive disease with PCV2. Again, I think this may be useful when we think about PCV3. We probably have cases of reproductive failure where you see maybe more clinical signs, but perhaps we're also dealing with some of these subclinical infections where there may not be a lot of pathology detected, but the virus is circulating and therefore infecting piglets. And I wonder if this is a good model for us to understand the epidemiology of PCV3 in herds, because to date, as you will see, there's very little understanding of how PCV3 is circulating within herds or between herds. So what would be the key things you need to think about if we want to diagnose or confirm PCV3? Well, number one is, I think, the weight of evidence is around reproductive failure. So if you're seeing an increase in stillborn pigs or an increase in mummified piglets being born, you definitely need to consider PCV3 on your list of differentials nowadays. And I think I use this quote. It's a colleague of ours in the US, Reed Phillips, and he was talking about PERS, but really, I think I use this quote, so good enough is not good enough anymore. Are you average? To suggest that if we look at averages when we look at reproductive performance, we may miss the picture. And why do I say this? Well, because I think we need to understand with particularly mummies and stillborns that this may not affect the population in a homogeneous way. So we're not going to see, like maybe we have seen with PERS, where you get a very widespread infection, high level of abortions, very clear clinical picture, or with influenza, where the whole herd is affected, sows get sick, fever, etc., then we see some abortions. This is going to be a much subtler type of picture with PCV3, a little bit like we see with PCV2. Some sows will have full immunity, some will be susceptible, and therefore you're not going to see a very nice average picture in your herd. That's why I think it's really important that we go back to basics, like Professor Segale said, and really dedicated time to looking at what the pigs are telling us, what the sow herd is telling us. So really, this is not new by any means, but really let's have a close look at what the sows are telling us in this herd. Have we seen abortions? Yes or no? If we haven't seen abortions, or we have, this can help us narrow down this very long list of differential diagnoses. This is a global list, by the way, that I've placed here. You're very lucky in Australia that many of these would not be at least high on your list. You should never forget them because things can change. But in parts of the world, particularly in Southeast Asia, the list of differentials is really quite extensive. If the sows are showing clinical signs, for example, fever, or they're off feed, this can already direct us towards perhaps a more infectious cause of reproductive failure. Are we seeing weak-born pigs in addition to stillborns and mummies? What's the pre-weaning mortality? Is that up, elevated before what we consider normal? How about sow parity? Is there a particular age or herd profile that we're seeing where we're seeing this reproductive failure? Is it happening across all stages of gestation or just in a particular period of time? All of these factors can really help us narrow down this very long list of differentials. And then, of course, is it a seasonal issue? Is it happening at a particular time of the year, or when we look at our records on the herd, it's a pretty much annual occurrence? And of course, importantly, what's changed in the farm? Are we undergoing a herd expansion? Have we changed the source of genetics? Are we using a different AI source, et cetera, et cetera? All can be pointers towards the introduction of a new infection. And then, of course, all of these lab tests come into play, but you can't always run everything. So we need to create some sort of differentials to start limiting the scope of what type of lab diagnostics we need to use. I want to also highlight some key definitions that we need to use to really help us narrow down what we're talking about. Fetal reabsorption, for example, or early embryo death is really going to be seen on the farm as a reduced litter size, so less total born than you would expect, or perhaps irregular repeats, but you won't have abortions, for example, or you won't necessarily see mummies in those infections. While abortions very clearly need to be narrowed down to a definition of a loss of a confirmed pregnancy prior to 112 days of gestation. If the sows are farrowing early, then that's not an abortion. That's an early farrowing, which, for example, is a very typical sign of PERS. And a mummified fetus, again, important to differentiate, particularly when we're talking to people on the farm and we want them to help us identify what's going on. These mummified fetuses are clearly piglets that died in utero and had sufficient time to begin to dehydrate. And of course, they can be of varying sizes depending on when that fetus died. While the stillborn piglet is clearly, and you can see that in the picture above, it's a term fetus that was born dead. We can put lungs into water. If they float, they were not stillborn, they were born alive and then crushed or died shortly after birth. And it's really, really important, I think, when we are investigating these reproductive failure cases that, you know, in many situations, not all fetuses are infected. And therefore, it's important that we take multiple piglets from an affected litter. And we suggest 3 as a good number to submit per affected litter. And it's really important not just to submit one, because that one litter may, or that one sow may not reflect the situation on the herd. So we recommend 3 affected litters to be submitted to the lab. And again, in areas where shipping of samples to the lab can be complicated, you can freeze fetuses, because for most intents and purposes, that sample will still be useful in the lab. So what typically can we see? And the most typical causes that you need to keep top of mind for increased mummified fetuses would be porcine parvovirus and PCV2. So don't immediately assume you've got PCV3 if you see an increase in mummies. Both of these diseases are still very much present and can cause problems in vaccinated herds if they're not correctly carried out. The other important thing that can allow you to start narrowing things down is that neither PCV3 nor parvovirus nor PCV2 are likely to cause abortions. And so if abortions are one of the key clinical findings, you already are probably moving towards a different cause for this reproductive failure. And the other thing that's important is when you have mummification caused by these viruses, by the parvo or PCV2, typically you have a very high amount of virus detected in those tissues, while with PERS, you may get mummies and very low viral detection. So there are some differences that can allow you to start narrowing down the cause. I show you this as a guide, and for many of you, this will be, very, very well known. But if we understand what we're seeing in the context of the stages of gestation, we can really understand quite well, or narrow down quite well, what our potential causes of reproductive failure are. So you've probably seen this a million times. It's the duration of the pregnancy in a sow and the typical pathology or clinical picture that you will see at the different times. So if you have intrauterine infection at these different stages, you will see a different picture. And the classical story we use this for is for parvo, but it actually can be useful for any infection, including PCV3. So if we talk about parvovirus and we believe PCV3, really in the early parts of pregnancy, so until day 12, really we believe PCV3 is unlikely to cause any relevant clinical consequence based on what we know so far. There is some possibility that if you have PCV3 during this early pregnancy stage, that you will have death of some of those fetuses, and then, or at this stage, they're embryos, and then you either have a reduced total born, or perhaps if many are lost, you would have a loss of that pregnancy and irregular returns. So again, you need to understand that, as far as I know so far, irregular returns to estrus and low total born has not been associated directly with PCV3. Death and mummification, which is at any time between day 35 of pregnancy and day 70, will result in these mummified piglets that you see at term. And of course, depending on when in this period of time the infection occurs in that individual fetus, you will see mummified piglets of different sizes. And then finally, if infection happens in the period between day 70 and day 114 of gestation, that's when you will start seeing stillborn pigs or weak-born pigs, because the virus is affecting the viability of those pigs. And this is a big difference between parvovirus and PCV3. With parvovirus, typically beyond day 70, the infection doesn't seem to result in much pathological impact. While with PCV3, this is aimed to be one of the key areas we see pathology. And this is a chart that you've all seen, I'm sure. I'm taking this from Mike Muirhead's Managing Pig Health Disease, book familiar to, I'm sure, all of you. And it gives you a kind of a scale to allow to calculate, or at least estimate, the time of infection based on the rump length, head to rump length measurement. Again, many causes can be associated with reproductive failure with increased stillborns and mummies, and just include this list, including non-infectious causes like mycotoxins should be on your list. In my experience, globally, chlamydia, lepto are relatively rare, but maybe in Australia you see more of that. And in most countries of the world, the three top viruses are parvo, PERS, and PCV2. And now I think we need to include PCV3 in this list. One pathologist shared me some tips that can maybe help us narrow down this long list of diagnoses. And one would be that typically fetal death between days 40 and 70 is associated with a viral cause based on their experience. Again, be careful looking at averages when you're looking at the herd. You know, 3 mummies or stillborn per litter is probably an intervention level in my estimation. And a tip that could be useful also if your lab is far away and it's difficult to get fetuses to the lab, is to collect thoracic fluid from these, if you can, and submit that instead of sending the complete fetus. I think this is an important slide, and I want to share it with you. This was a part of a presentation that Dr. Bailey Arruda from then Iowa State and now NADC shared with us during a virtual perspective webinar we did. And I basically copy-paste her slide because I think it's really a very nice working case definition that allowed them at Iowa State to really create these very well-defined PCV3 cases. And so they use this criteria to guide their coding at the lab. And basically they have 3 disease groupings depending on the age of the animals. If they see stillborn and or mummified fetuses, they identify high levels of PCV3 in those tissues, or they detect it by in situ hybridization. That is a PCV3 case in their estimation. If they discover it in weak-born normal suckling piglets, and they see this lesions, particularly this perivascular inflammation, and they detect high level of PCV3 by PCR, they call it a PCV3 case. Or in growing pigs, if they again see lymphoid lesions with this perivascular inflammation, and again a high quantity of PCV3, they also will classify that as a PCV3 case. So again, very important to have full lab backup to really confirm cases. When narrowing down on PCV3 reproductive descriptions, they are using some criteria that I share here. Again, increased mummies and abortions without, mummies and stillborns without abortions, typically in young parity animals, typically in animals or fetuses with a 7 centimeters to 30 centimeters crown rump length. And they, as I say, using that criteria, were able to confirm reproductive failure associated with PCV3 really all over the US and even in Mexico based on their criteria. And what they tell me is that they find the virus in very, very large quantities in those confirmed cases. This is not a case of a low-level detection. The virus is present in large amounts. So in summary, if we want to diagnose PCV3, we really need to select litters for submission under a very solid case definition. I would use 3 cases or litters that have 3 or more mummified or stillborn piglets. I would submit multiple of these affected fetuses. I would carry out histopathology. If you can, do PCR for all of the main viruses that are associated with mummified piglets, and perhaps not next generation sequencing if your lab has capabilities for that. In the US, this is now very affordable. In other countries, it's really not available for diagnostic purposes. And then if you do have abortions, number one, PCV3 is probably less likely to be involved, but then sow samples, so blood, placenta, or tissues associated to the sow would be relevant for diagnostics. Serology for PCV3 is really not well understood and probably not recommended at this stage. The area where there's really very, very little information is around epidemiology, transmission, how is herd immunity happening? Is this an issue with subpopulations? Is it an issue of startup herds? Is it a variant of PCV3 that enters a herd as a new pathogen? We really don't know. This is the part that really is a blank canvas right now. The understanding based on these cases that have been well described is that perhaps because we're seeing it in low parity animals, this is an issue of lack of immunity in new entered animals into the herd, gilts in particular. And therefore, this debate whether, gilts, high health gilts coming from outside are naive to PCV3 and become exposed during their pregnancy and therefore show the clinical signs. But this is speculation right now. Other summaries that we can make from the literature and the information we know so far is that really the virus appears to be genetically quite uniform. So it's not like the new PCV3 strain appears out of nowhere and changes the pathology of the disease. We do know very, very clearly that PCV3 is genetically completely different to PCV2, at least at the ORF2 level. And therefore, we have to assume that PCV2 vaccines are not going to provide protection against PCV3. And the question we in industry, in the pharmaceutical industry are trying to understand is, one, does this disease become relevant economically? Is it more important than other infections, and should we develop then vaccines to solve the clinical and economic cost of PCV3, or perhaps management of acclimatization and herd immunity through just better exposure management is enough? This is really a wide open question that we don't have clear answers for. So in summary, lots and lots of publications in the literature. I did a quick count, and 126 peer-reviewed papers on PCV3 since December 2016. And there's probably more. I probably missed a few Chinese papers in the list. It's widespread in the US and everywhere else. And it's typically seen in countries where we have these endemic infections like PRRS and PCV2 in co-infections. There has been some very clear clinical associations now with a number of diseases, and in particular, reproductive failure, in my mind, is very clinically relevant and consistently identified and described. And so I really believe that PCV3 is a pig pathogen. It is causing disease, particularly reproductive failure, but really the relevance, clinical relevance to you guys in the field is still unknown. Is this just another virus that we should have on the list as a minor importance, or is it really clinically relevant? We don't know. And of course, as a pharmaceutical company, if these relevant pathogens economically, then it's imperative that we develop a vaccine solution. And of course, this is something that we are researching in BI. Now, when you talk to scientists, and maybe this will be part of the Q&A, some will tell you this is not real. This is not a real pathogen of pigs. It's endemic. It's really everywhere, right? Well, so is rotavirus, so is PCV2. But really, we know that in endemic infections, a subset of animals can still become clinically sick, even if their pen mates or other pigs on the farm appear to not have any clinical outcome, negative outcome. So I think that's not enough to exclude PCV3 as a pathogen. Number two, people will say, look at the studies that show that it's been around forever. It's not a new pathogen, right? Well, that is true, but PCV2 was also around for a long, long time before we saw the PCV systemic disease. So, what has changed? Has prevalence changed? Is this a case of a human contribution? Have we changed the herd management in such a way that herd immunity has waned and allows the infection to take hold? It's really hard to know that part. And then finally, all of you know many, many cases where you've had reproductive failure and you never could really get to the bottom of the cause for that reproductive failure. And perhaps those were undiagnosed PCV3 cases. And the same would be said with PDNS. Many, many cases of PDNS where you couldn't identify PCV2, for example, and remained unknown in terms of their cause. So perhaps those unknown cases were PCV3 cases also. So I think we need to keep it in mind on our list of differentials for both reproductive failure and things like PDNS. So my conclusions and my take-homes for this talk is it's a pathogen of pigs. It causes clinical disease in some of the pigs it infects, but it doesn't appear, with the evidence to date, to be associated with either enteric disease, a primary respiratory disease, primary pneumonia, or even a primary wasting disease, or PMWS. So with all this in mind, the key question to date is, what is the economic impact of the disease? We really don't know that. With that, Andres, I finished my talk. I hope I didn't go too much over time, and open for questions in the Q&A session.
Thank you, Oliver, and your presentation really provided a lot of information that we didn't know, and I sent you and Professor Segale some of the questions from the participants that they provided ahead, and you have answered a lot of them. Professor Segale has also answered questions throughout your presentation, but we have a couple from the first presentation that I would like to probably raise now. So we have one from Dr. John Carr, a good friend of both of you, in relation to how can we have low antibody levels in PCV2 positive pigs? Is there a case of tolerance?
Not really. In fact, tolerance or immune tolerance has never been described in circoviruses or specifically in PCV2. So when we have low levels of antibodies, is basically related with the fact that those animals have not been infected by the wild virus, so that has been minimal circulation, and this happens in a number of batches, sometimes of animals that have been vaccinated, in which the infectious pressure is low. So at the very end, when you have low antibody values, is mainly because of low infectious pressure. Certainly subpopulations may account, and especially when we are talking about piglets and young piglets, it could be related also with colostrum intake. deficiency in colostrum intake, of course, is a good reason for having low antibody values on antibodies against PCV2 or against whatever other pathogen. However, this is very, let's say, important to take into account, because if the problem is colostrum intake, then sometimes we like to vaccinate with the lower antibody values, the better. And this is not necessarily the case, because low antibody values could mean problems in the farm, really.
Probably a follow-up question as well. What level of PCV2 qPCR is required to stimulate the immune system?
Well, at the very end, PCV2 is an ubiquitous virus. It's not necessarily a huge amount of virus for infecting the animals. In fact, many years ago, it was a study trying to see which is the minimal amount of virus necessary for infecting a pig. And for example, of course, measured with PCID50, which means infectious virus, with 10 to the 2, it was more than enough to infect a pig. However, we are used to work with quantitative PCR. So quantitative PCR doesn't really measure infectious virus. It means copies of genome of PCV2. And the correlation between one or the other is not evident, because when you have 10 to the 2 or 10 to the 3 in PCID50, might be you have 10 to the 7, 10 to the 6, or 10 to the 8 in quantitative PCR. So those are not, let's say, directly comparable techniques. So with a certainly low amount of virus is enough to infect an animal.
Very good. All your questions have been answered by you throughout the presentations, and I really thank you for your generosity. I would like just to finish with a quick just a slide on some coming seminars that we will have in July and October. So one on enteric diseases of pigs in July this year, and then we will have another one in production economics. On behalf of BI, I would like to thank you for your attendance, and especially to the two presenters for your generosity and your time. I would like to thank all the team within BI, going from BMS to sales and marketing. They really helped putting this together and sending invitations to the attendees, and obviously to the global Circoflex team for their support and helping me with this event. I really hope to see you during our next seminar, and yeah, please stay safe. If you have any comments, please don't hesitate to contact me, and I will pass that information on to the panelists for tonight. Thank you so much, and have a great night.
Thank you, everybody.
And thank you very much, Beringer, for the invitation. My pleasure.
Thank you so much.
Thank you, Kim. Always appreciate it. Always learn from hearing you present. Thank you.
No, by the way, you did a great presentation on PCV3. It looks like that you are working with PCVs in a very important form.
Well, we have some interest in PCV3, yes.
See you guys.
Also. So
thank you so much.
Okay. Bye-bye. Have a nice day.
Bye-bye.
Happy Easter.
Thank you, everybody.
Bye.
Bye, John.